it seemed to be making some argument about springs and how inefficient springs are. I don't know what number you come up with, because you don't really pin yourself down to any sort of statements, therefore you can't be challenged on it. So I don't know what percentage you're saying. I think Mindless Marbles mentioned that you were saying they're about 70% efficient. Where you come up with that number, I don't know, but obviously you can test these things. So if we were to take a mass and compress it onto a spring and then let it launch up, it will reach a height, and the height it reaches comes from the energy of the spring. That's a fact. You know, you compress the spring, you let it go, boom, and it goes to a height. So the energy came from the spring. That's how it got there. Then when it gets there, it's in gravity then, and it's going to fall back down. So the potential energy in the spring converts to kinetic energy. It goes up, and that stores as potential energy in gravity. Now it's going to fall back down, and as it comes down, it's going to land on the spring again. Now, if your claim is that it's the 70% inefficient, so as this is launched up, if there's, say, 100% of energy here, and only 70% of that energy goes in to launching that mass to that height, as it comes down, there won't be enough stored potential energy in gravity for it to compress the spring anywhere near down to what the original compression was of launching it. You know, you should see some significant difference. You know, as it comes down, it's going to be, you know, there's going to be some visible difference that it's not compressing the same because there was a loss of energy when it was launched. Obviously, there is going to be some losses because we have air resistance and we have friction. You know, it's not a frictionless environment, and obviously we've always got air to contend with. So there's going to be some energy losses, some percentage. I don't know what that would be. Again, I could just do like you, could just come up with a figure. I could say, oh, you know, that you're going to get, you know, 20% loss or 5% loss, you know, could just make a figure up. But, you know, realistically, there's going to be some energy loss as we launched up, because it's, you know, it's going in the up. It's travelled up there with some friction and air resistance. It's travelled down with some friction and air resistance. So it's not going to be perfect, but you're saying there's a good, you know, 30% loss in efficiency. Again, don't know where you come up with that number, because I'm pretty sure you haven't tested it, because you don't test anything. You just pluck numbers out your head, you know, and make statements that suit your argument. You know, I suppose in your world, if they were 70% inefficient, it would, you know, play to your ideas. But again, these things can be tested, so we'll move to that. This footage is from another experiment, but I thought it'd be useful here. So initial, I'm calling 0.75 centimeters, and then it's launched. The energy from the spring converts to kinetic energy, which will raise it to a height. I'm calling that at 7.5 centimeters, so that's its maximum height. Now I've froze it, you know, I haven't anti-gravity here, I've freeze framed it, and it will drop back down. You're saying it's 30% inefficient. As you can see there, yes, there is a little bit of a gap, there is some loss, but it's certainly not 30%. And then obviously it's going to bounce back up, and that will show us how much energy there is left there, and I'm calling that at 7 centimeters. So we've roughly got a difference of half a centimetre, 5 mil. Again, I froze it there, we're not doing anti-gravity, and then it's going to drop back down after that, the slow-mo runs out. So just add here that obviously I was taking the measurements roughly from the centre of mass, so centre of mass initial to the centre of mass final. Calling the initial start position 0.75 centimeters. We've got a travel of 7.5, so we take the 0.75 off the 7.5, and that gives us 6.75 distance. So that was for the first launch. As it came down and bounced again, we'll go with the same initial because it was practically there, and it got to 6.2, got to 7, so minus the initial, we got a travel distance of 6.25, so there's a difference of half a centimetre, 5 millimetres, however you want to say it. So the two distances, so 6.25 divided by 6.75 equals 0.9259, which can round up to 93. So 93%. So after the initial launch, and obviously incurring some friction there, coming down, incurring some friction there, resistance there, getting back up, and again incurring friction, we have 93% efficiency. So which is nowhere near the claim of, you know, the 70% efficient. So you're saying a 30% loss just by launching it. This has been launched, gone up, come back down, and relaunched, and we're still at 93%. And this is evidence. This is a proof. You know, we're not talking about fuzzy wuzzy feelings here. We're talking about data points, actual real world evidence. So your claim of spring inefficiency doesn't hold, does it? Also, I forgot to mention, obviously, the weight of the mass. It's less than 25 grams, so not heavy, not, you know, I don't know what your class is light mass. You know, if we've got to extract some atoms and launch them, I don't know if we've got to go that light, but in my mind, 25 grams isn't particularly heavy, because your contention was the lighter the mass, the less energy would get into it. And clearly that's not the case, is it?